Integration of Water Resources Engineering with GIS and Simulation Models. 6 courses in 1 diploma. Water resources are at the heart of sustainable development in many regions of the world. Water of sufficient quantity and quality is an essential resource for agriculture, industry, and tourism, but also for everyday life in cities and villages. A growing population and a growing economy not only lead to increasing demand for water but also cause increasing pollution that may threaten the very water resources this growth depends on and thus threaten the sustainability of development. Water resources are distributed in time and space, and their availability may vary greatly from time to time and from place to place. This variability causes problems: not enough or too much, drought or flood, and not of the right quality. The basic unit in water resources management is the river basin or hydrographic catchment, and the network of draining channels, the river network that collects and conveys surface water. The river reaches, dams, and reservoirs, diversion and pumping stations, waterworks, and secondary distribution networks are all spatially distributed elements of the system. Underneath, we find the unsaturated and saturated zones of groundwater aquifers, usually contributing considerable quantities of high-quality water with quite different, much slower storage and flow characteristics. The elements of water resources management are distributed in space. Their location, surrounding, and spatial relationships are critical for the resulting flow characteristics and the quality of the water resources and thus their availability for different types of use. River basin management has apparent spatial dimensions since it is focused on a spatial unit, the hydrological catchment, in the first place. Consequently, geographic information systems are one of the tools that can be used for their analysis. This makes the use of GIS, its integration with traditional water resources models, an obvious strategy for the development of river basin management systems. While the GIS is used to capture, analyze, and display spatial data, the models provide the tools for complex and dynamic analysis. Input for spatially distributed models, as well as their output, can be treated as map overlays and topical maps. The familiar format of maps supports the understanding of model results but also provides a convenient interface to spatially referenced data. And expert systems, simulation, and optimization models add the possibility for complex and dynamic analysis to the GIS. One major challenge in building effective river basin information systems is the integration of dynamic models with the capabilities of GIS. The GIS can provide a common framework of reference for the various tools and models addressing a range of problems in river basin management, supply distributed data to the models, and assist in visualizing spatial model results in the form of topical maps. In a multimedia framework, it can also provide a common interface to the various functions of an integrated river basin information and decision support system. This interface has to translate the data and model functionality available into information that can directly support decision-making processes. Historical data of rainfall, river flow, and air temperature, as well as water quality, are stored in the various monitoring stations. The hydrographic and hydrometeorological observation data are not only analyzed in their own right, but they also form the input for the various simulation models. A major problem for water resources management is droughts, prolonged periods of below-average rainfall that lead to low soil moisture, lowering of the groundwater table, and, most importantly, low flow in the river. This, in turn, leads to a combination of increased water demand for irrigation and low availability of irrigation water. Below a certain low flow level, pumping water out of the river in fact becomes impossible, and the pumps fall dry. The water resources model needs river flow at all of its start nodes, representing inputs. These can be well fields, where groundwater enters the surface water budget, or subcatchments. For the latter, a rainfall runoff model provides data for HEC-GeoHMS, but also the possibility for scenario analysis of land use changes or long-term climate change. Data such as catchment boundaries, elevations, slopes, land use, as well as rainfall inputs are automatically taken from the GIS and time series databases, respectively. Irrigated agriculture, and rice paddies, in particular, are the dominant consumer of water, by far exceeding industrial and domestic demand. The water demand in a given year depends on the naturally available water through rainfall, but also the areas and crop varieties to be irrigated, irrigation technology, the conveyance systems, example lined versus unlined irrigation canals, and operational control. Similar to the contamination of surface water, groundwater pollution can result from the application of fertilizers and agrochemicals. Waste management in the form of badly managed landfills is another potential source of groundwater pollution in the humid tropics. Meteorological and climatic data visualization and analysis are essential for researchers and forecasters to understand and apply these data. Such data are inherently spatially variable, and hence the use of a geographic information system, GIS, represents a useful solution for the management of vast spatial meteorological and climatic data sets for a wide number of applications. The powerful mapping capability of GIS is a primary factor that makes it attractive to the atmospheric community. Layer-based visualization also supports the comparison of various aspects of a meteorological data set, and its spatial properties can be highlighted by incorporating geospatial information in GIS. With GIS technology, meteorologists can achieve more accurate weather forecasting, and they can use GIS to track dangerous weather patterns as well. Thanks to GIS technology, communities can be given early warnings of dangerous weather activity so they can prepare or evacuate the area. The purpose of water resources management is to mitigate or prevent the adverse impacts of excessive runoff or shortage of water. Hydrologic models have served as a valuable tool in water resources management for many years. Simulation models are usually used to predict the impacts of proposed land use scenarios and to evaluate management strategies. During the last several decades, the application of computers for the planning and operation of water resource systems has rapidly become an important field of research. Recently, geographic information systems, GIS, have gained much attention in many research fields, wherein the output can be displayed at a high quality and be easily understood. The tremendous progress in GIS techniques has led to significant advances in different types of physically based hydrologic models. GIS can offer spatial data management and analysis tools to assist experienced users in organizing, storing, editing, analyzing, and displaying local and attribute information about geographic data. However, the GIS is seldom the environment in which water system analysis methods are directly implemented. This is especially unfortunate in the field of water resources planning and management, where mathematical models are important tools to provide insight into water resource problems. Obviously, model applications could benefit from the spatial analysis and display capability of GIS, and GIS could benefit from the modeling capability of mathematical models. Melding the strengths of each will result in more powerful tools for the planning and management of water resources systems. Most hydrologic models in current use, such as SWMM, Storm, HEC-1, HSPF, Sacramento, and PSRM, are conceptually based on lump models. These models were proven to be efficient in water resources management. However, this kind of model usually devalues the spatial variability within the catchment. In order to improve the quality of hydrologic models by including the spatial variation of watershed characteristics in the modeling process, distributed hydrologic models have gained much attention recently. Simulation models in water. Resources engineering. A simulation model is a mathematical business model which combines both mathematical and logical concepts that tries to emulate a real-life system through the use of computer software. Types of simulation modeling in water resources engineering. 1. Hydrologic modeling. 2. Hydraulics modeling. A hydrologic model is a simplification of a real-world system, example surface water, soil water, wetland, and groundwater, that aids in understanding, predicting, and managing water resources. Both the flow and quality of water are commonly studied using hydrologic models. A hydrologic model is a simplification of a real-world system, example surface water, soil water, wetland, groundwater, estuary, that aids in understanding, predicting, and managing water resources. Both the flow and quality of water are commonly studied using hydrologic models. Hydrological models predict discharges at a certain site within a catchment area from rainfall data and terrain characteristics, including soil types, land cover, drainage infrastructure, and elevation and derived parameters such as slope. Popular mathematical models. Regression method, linear, nonlinear, ARIMA, etc. Finite element method, 1D and 2D. Finite difference method, 1D and 2D. Finite volume method, 1D, 2D, and 3D. Heuristics competing methods, artificial neural networks, ANS, support vector machine, SVM, gene expression programming, GEP, decision tree, random forest, etc. Hence, The idea of making this diploma, integration of water resources engineering with GIS and simulation models, that explains advanced methods in dealing with simulation modeling programs in water resources engineering, and how to obtain and prepare all the completion requirements for these programs, thus providing all that is new and advanced for specialists, researchers, and students in the field of water resources and the completion of projects in a professional format through making the integration of water resources engineering with GIS and simulation models by using computer programs for hydrological and hydraulic modeling in addition to programs for modeling different irrigation methods. Water use in agriculture is at the heart of any discussion of water and food security. And implicitly, the diploma is concerned with calculating, finding, and estimating all elements of the hydrological cycle, using the best methods and criteria. Follow us step by step from one part to another in the diploma.